afternoon, everyone. Welcome in the SEFI Special Interest Group SEFI at Work session in our series of methods in engineering education research. And so it's very nice to see you all here and that you're probably spending some of your lunchtime to hear about the methods in engineering education research. Yes, Claudia, go to the next one. So this series is being offered to you by the Special Interest Group of Engineering Education Research, and in particular, these are the three people that are taking the organizational matters into hands. So we have Jan, who will probably be waving to you right now. Yeah, Esther, and me. So the focus of our series on methods in engineering education is on research methods in engineering education, and we do help you to learn more about its research methods by giving the floor to a researcher who had a high impact publication with some solid methodology. So if you're already invited by this, it is a real honor, of course, to do. And we're very happy so far that people are seeing this as an honor and then accepting our invitations. So the challenge that we provide people is that we want our speakers to give some insights in these engineering education research methods, because we know that the engineering education research community is growing, but we also know that people are still quite scattered around. And sometimes we miss like this conversation that we can have with close colleagues on a methodology. So if you're going to this series, we hope you will not only learn the things you will be able to learn if you read a paper or if you read a handbook, but also the things you would learn from your colleagues if you're chatting at a coffee machine about the frustration with the methodology you have been using or whatever. So also don't hesitate to ask our invited speakers about these challenges. So we will hope you will get some insight in research methods that goes beyond textbook information, and you will get these from well-respected researchers and authors. And of course, in these seminars, you can always connect with other people in the community. Today, it's my pleasure to announce to you Christian Kautz and Claudia Scheffler, who will be presenting on student reasoning. We will also be announcing the best research paper seminar later, but that's for the end of the seminar, and that will be done by Esther. Also, if you have suggestions of other things you want to learn in this series, you're always welcome to contact us, and then we will look for an interesting speaker that can cover the topic. So now the floor is to you, Claudia and Christian. I think you have to unmute, Claudia.
Oh, sure. Okay, thank you, Tine, for inviting Christian and me and to present our work on student reasoning in hydrodynamics. So something special in engineering in the engineering field. And we had this publication 2021. And yeah, we will try to give you some insights and a little activity also. And who are we? So I'm Claudia Scheffler. I'm from the Technische Hochschule Rosenheim. I did traditional physics, so to say, and also a postdoc in Australia. I worked in industry for 5 years, and I'm a professor for physics, and I'm teaching engineers mostly. And but I'm also doing didactic projects since 2012, and I'm into these, I learned about physics education research from Christian, and I thought this is a very great thing that we, and this is one part which we then did together. And I'm now since 2021 at the, so to say, BITES in Munich. It was the former DITS, it's the Didactic Zentrum. And there's a group for teaching and learning research. And with half of my job, I'm working there also.
Okay, my name is Christian Kautz. I'm also a physicist by training, but already switched into physics education research during my doctoral work. after another position in the US, where I also did my doctoral work at the University of Washington, then later Syracuse University. I came back to Germany and to Hamburg, Hamburg University of Technology, now 20 years ago. And my focus basically since then has been to look into student thinking in our introductory courses, which we know cause problems for many of the students, are a big hurdle, at least for some of them. And the idea is to find out what are these difficulties that students have.
Yeah, and we would like to also get to know a little bit about our audience. And we would like you, just as the poll tool doesn't work at the moment, just write the number if you want to. Who are you in the chat? So if you're a student, PhD student in engineering, education, research, or in other fields, a researcher or a lecturer, someone else, just write the number in the chat, and then we get an impression who is here. Thank you.
Okay. There's some 4s, 2s, 6s, and 5s. Okay, so we have a very diverse audience, which is very nice to have.
Yeah, thank you.
Okay, thank you very much. I hope we have something interesting for every one of you, regardless of what your position is. We can then start looking at, Tina, should we just read the question? And
no, I can read it for you if you want. So the format we have is that we put some questions forward to the researchers and we try to get them similar over the different talks. So the first part is the challenge and the research question you already came up for your paper. So what is the problem, challenge you try to tackle, and why is it important?
Okay, thank you. Well, the basic challenge, I think, is a very general one, and is one that many of us are familiar with and who work in engineering education in one position or another. And that is that student learning is often less successful than we want it to be, than the students expect it to be, than we expect it to be. And it's very clear that there are a large number of factors that play a role and that may be together causing this phenomenon. There are social factors, there are personal, individual factors, things that have to do with society, and so on and so forth. What our approach is to look at one particular component of that broad problem, and that is how do students think about what ideas do they have about the subject matter in particular courses. It's been our experience, and the next slide actually shows an example of that in many introductory engineering courses, technical courses, student thinking actually plays a large role and is worth being investigated. And what I'm showing you here is an example for this approach, but at the same time also the starting point for our particular work in this case. Because it is work on hydrostatics, which in a way often in the courses comes before fluid dynamics or hydrodynamics. And in this particular example, in the diagram that you see is an excerpt from an exam question where students were asked to rank pressure, hydrostatic pressure in a body of liquid. In this case, it's mercury, not water, but that doesn't change the principle in any way, at various points. So there are marked points, G, which is sort of hard to see because there's a line going through. There's X below, and Y and Z at the same altitude, same height within that body of fluid. And what students have learned by the time that they were, or should have learned, were taught by the time they took this exam, is that in any connected body of fluid, the points that are equal height actually have the same pressure. So students should recognize that X and Y and Z have the same pressure. And at point G, the pressure is lower because it is higher up in that same body of liquid. On the other hand, what you can see from the sketches that the student has drawn, this particular student used a different approach to solve the problem, one that turned out to be incorrect, in that the student literally interpreted how much liquid is there immediately above the point that I'm looking at, and therefore comes to a different ranking where Z has the lowest pressure and Y is somewhat greater pressure and G is still greater pressure and X the largest pressure. So for one thing, this is sort of an illustration of our approach. Ask questions about a specific situation where students are supposed to use some principle that they learned in that course, in this case, Pascal's principle and the depth relationship of pressure in a liquid. And at the same time, it's also basically our starting point for the research we're presenting to you now. Our ultimate goal, that was the last line in the previous slide, is that we use these results to design instructional materials, because if students the experience has been that if students are led to struggle with these particularly difficult issues, they learn better, and their understanding will develop better.
Okay, so the next question that's coming up regarding the challenge and the research question is, how did you translate this particular problem and challenge to the research questions, and what are they in fact?
This comes from my part. I taught many students in hydrodynamics, and we have a lab course and we have an experiment there. And we are having a water tank up here, and we have water flowing through that pipe. And then we have manometer pipes here, and it's open, and students measure the volume flow here, and they measure the pressure drop here. And then they can calculate if it's laminar, or they measure a graph, and so on. And in the beginning of our lab, we always talk to the students. And when you talk to them, you really find out in an informal way that they really don't get a clue what this means really. What does water flow in here or not? Or what does it mean? Is the water accelerating? Is the water... So they didn't have a really good understanding of that. And I was already working with these tutorials, and I thought this is interesting. And so I called Christian and we started that project. And he said, well, that's interesting. And we want to go deeper in how students think of a situation like this, or a situation where a pipe diameter narrows more. Okay. And so we come up, we have this informal observation from a systematic point of view in a laboratory course. We have a lack of conceptual model for pipe flow even after instruction. And we posed a hypothesis. Our hypothesis was students have difficulty distinguishing between and understanding the relationship of continuity principle and Bernoulli's principle, and also the role of friction. And from this, we started with our research question, which is much more specific, because we did that at our place. To what extent are students in an engineering degree program at a German University of Applied Sciences able to apply the principle of conservation of mass, as expressed by the continuity equation, to simple situations of incompressible fluid flow? In particular, is their ability to apply this principle sufficiently robust for them to successfully do so even in the presence of distracting factors in the problem settings such as influence of gravity, dissipative effects, commonly referred to as friction, or a visible pressure drop? And what patterns of reasoning do students display in this context? So this was our goal. So we want to have, do they apply a conservation of mass properly, even if we distract them with other influences? Especially friction is a big thing. Okay.
So the next part we will be tackling is a methodology part. And the question we have there for you is, how did you go about choosing the methodology to address the research question, and why this methodology in particular?
Okay. When thinking about researching about this question, you can certainly start by introspection and wonder, why might this topic be difficult? But essentially, we need some empirical method here to probe student thinking. We cannot observe directly what they think. We cannot look into their brains. So we somehow have to induce them to actions that we can observe, that we can interpret. And the three most obvious options, I think, that we have for that very generally are: we can observe student interaction with each other. We can observe their behavior in the classroom. So that would be sort of in vivo research in the live classroom. We can do interviews where we ask students to come separately to talk to us, usually individually, but we could also do that in groups. And we can sort of do that in a written form, still within the usual instructional context, by asking written questions on examinations, on little tests or quizzes that are usually not graded. Having these questions not graded has the advantage that it doesn't affect students' grades in any dramatic way, because we do ask very challenging questions, or questions that at first may look rather simple, rather straightforward, but often turn out to be quite difficult for the students. In this particular case, we chose written questions. Next slide, please. For the reason that with this method, we could get large numbers of data. We could give the same kind of test in different courses. We could therefore also differentiate by different instruction styles that are used in those various courses, or by different prior instruction. We had courses where students had prepared themselves for the lab experiment without any lecture, just by reading some manuscript or text. We had courses where students had gone through lecture instruction on that type of topic already, on that topic. And we had courses where not only lectures, but also more interactive forms of teaching had taken place about the topic that we asked them about. It was economic in the time sense that these written questions could be integrated into the normal instructional context. In this particular case, I think in most often they were given at the beginning of this lab experiment. It took 5 minutes. Students could think about this, hand it in. There was no grade pressure, not really a time pressure either. If somebody took a minute longer, that was fine too. We then could do the coding with these written artifacts that students produced at a later time, and we could do it ourselves. We didn't need to hire anybody that we needed to train with this. Okay, I think, Claudia, you want to introduce the activity already?
Yeah. Okay. Yeah, and to give you a feeling for what we did, we said that we thought that we will want to invite you in this short time. And therefore, we choose a Padlet that always works. And here's one of the questions we posed to the students. And I give you I try to do it in the chat.
I'm just trying to.
Oh, can you do that, Christian?
Yep. Hold on, I just make sure everybody gets it. And this should be the
link for the chat. Yeah.
Link.
And there you find, I can also maybe share what is this then. Here you find the question we posed, and you find also one answer that is almost correct, and we've got 3 answers that are incorrect. And we would like you to invite you to choose. We will send you in breakout rooms, and we would like you to choose one of these incorrect answers and try to find out which misconception do you find, and then post it here on the Padlet just by putting the plus, and then a post goes, and then you also submit the post. And then we have here things that you can find. If you have more time, you can also analyze too. And maybe it's good if I explain the situation. Or
we plan to take 10 minutes for that.
Yeah. I mean the question 1. Shall I explain the question as well?
Yeah, go ahead.
Yeah. Okay, you see it? Okay. So question 1 is an inclined pipe question. We call it IP because the water goes up. Water continuously flows out of a wide water-filled tank through an inclined pipe with uniform diameter. The water level of the tank is kept constant by a refill mechanism. Consider the water flowing in the pipe. Is the velocity of the water in the middle of the pipe at position 2 greater than, less than, the same as the velocity at position 1? Please explain why this answer is correct. So, and you should now look for the cross and the explanation, and then post it in the Padlet.
And to make the job a little easier for you, we posted on the Padlet besides our paper, the question that Claudia just showed, and student answer, student response 1 that we considered almost correct, as well as 3 others for you to analyze. All right, so maybe let's briefly look at the postings here. Somebody commented on student response 2. The student does not think about the continuity of the flowing water. He or she does think that there's a pressure counteracting the movement of the water, and the pressure is lower the further up the pipe you go. So some assumptions about the pressure may actually turn out to be correct, but the model underlying this is that pressure is counteracting the movement, and even though there is a connection between the pressure and the motion of the water, it is depending on the pressure gradient, and therefore a little more complicated than what a student assumes here. The student response 3, pressure is not taken into account, which in itself would not be a problem, because the idea is that students answer here without an assumption, making an assumption about pressure. And a principle is the conservation of mass is not taken into account either. That is part of the problem that I believe is the case in here. When in another principle is invoked here, I think student 3 is the one who talks about conservation of energy. And that, while that is a good principle to use when you talk about the motion of a solid compact object, it is more problematic to use, more difficult to apply in the case of a fluid. And what basically is behind student 3's answer is that the student is conceptualizing the motion of the liquid just like a single object, a ball that we would throw, that where indeed at different times through the motion, potential energy and kinetic energy trade off. Now, response 4, somebody wrote misconception. There's a direct link in this case between static pressure and velocity. Yes, that in a way is an incorrect assumption. There is a connection between pressure and velocity, but it involves actual 3 different things and not only 2. So if I only use 2 of these to argue from one about the other, then I'm losing sight of something important. And actually the way out of this problem is by invoking the principle of conservation of mass, so this continuity equation, which students often do not do here. student connects pressure to driving force and then velocity and does that incorrectly. Misconception about reality as a result of this reasoning would be that there's fluid stacking up. There's a fixed diameter, so different velocity would mean that the water should be compressed, what is not happening. That's correct, a correct comment, remark, thank you, that the water is being considered incompressible here, and for that reason, we can imply that equal cross-section means equal velocity at the various points, regardless of whether the tube is at an angle or not. If the crossed out answer, the student seems to see somehow that the velocity is constant, but can't connect it to the pressure not being constant. Yes, and that's a very interesting observation that we very often have that in such quizzes, that students start out with an answer which may actually be correct. In this case, it was correct, but not for quite correct reasoning, one have to say, but it was the correct answer, and then start thinking more and can't fit things together, and then switch to a possibly incorrect answer. But it is a fact that students can't reconcile different ideas that they have about the situation. Thank you, Claudia, for showing this. That actually tells us that they have not really thoroughly understood the principle that is supposed to be learned here. Let's maybe go back then to, or do we have another one that we want to comment, or go back to the slides?
Or does any one of you want to comment or ask a question?
Yes, there is a question. Go ahead and speak up. There was a question, I believe.
Yes. I just wanted to comment, like, how many such similar exercises do the students do prior to taking the test?
In our investigation, we gave them 2 questions. One question with the inclined pipe, and then we have 2 types of question. One with a straight pipe, and one with the manometer pipes in it, and one not. If you're interested in the question, on the left-hand side of the Padlet, there's the paper, and you can just have a look in the paper also. Then you see the 3 questions. So it was only a 5-minute test.
Okay. But my thought was, if we move on to the test, is it a continuation of the discussion taking place in the class, in which they are learning to integrate various aspects of mathematical analysis to the fluid dynamics problem, or it's a step up from the general classroom discussion? That was what I was thinking at the back of my mind.
I think that's a question also about the prior instruction that the students had, and that was different for the different groups that we sampled. So we had students which basically had no classroom instruction about the topic, and had prepared for the lab experiment on their own. And on the other hand, we had students, several groups of students, where actually the material was discussed in detail, and the principles underlying these phenomena had been discussed in the classroom already. So that for some of the groups, one would have expected that they are able to answer this at this point, also at the level of mathematical expertise that is needed here. And for one of the groups, we actually would not have expected that, but wanted to figure out what their ideas are that they come with into the classroom after reading on their own.
Okay.
Thank you.
Did this answer the question?
Okay.
Okay, then maybe let's move on to the
proceed. Yeah.
Okay. Was there another question?
Yeah, I think Julie had another question. Do you have a quick one?
No, I just had the impression that the previous question was misunderstood, and I wanted to clarify, but that was done by Abel himself. So that's it. Thanks.
Thank you. Yeah. Okay.
Thanks.
Regarding data analysis, we did a quantitative analysis of the answers and explanation. So answer is the correct cross, if it's correct or incorrect. And then we look for the reasoning, if it's correct, incorrect, or missing. And the details are in the paper. You can just get the graphs there. And the qualitative analysis of student reasoning, this is the much more harder part to do. So we had initially identified for each question an initial set of 4 to 6 types of answers. So we try to find out, how do they argue? Do they use Bernoulli? Do they think force causes velocity, or what's their thinking? And then in a second round, we coded each answer according to the predominant idea. And these 2 things, they were done. We had lots and lots and lots of thinking and discussion doing this. Note, some explanation used more than one idea, and a few could not be classified at all. So some is really not clear. And third, what our goal was, we could characterize each student's misconception. We could say this student has this misconception, this or fluid flow according to the idea used in the entire test. So we had these 2 questions, and we tried to say this person understands continuity, this person uses always wrong assumption and pressure or whatever. But this didn't work for us in inconsistencies of student ideas across different questions. This proved to be not useful for our goal. And therefore, we changed it and we said, okay, now then we don't analyze each student, but we analyze what types of reasoning occur. So focus on assumptions of use and inferences drawn by the students. And then we try to generalize these to identify characteristic patterns for student reasoning. So there are students using Bernoulli, there are students using force or whatever.
And maybe as a quick comment on the practical process of doing this, what I found helpful at some point is printing out the student answers onto small slips of paper and then just sorting them according to the category that we find in them, which then allows you to sort of, in an analogous way, analog way, not a digital way, to scroll through different answers that we thought were similar and check if they really are. Unfortunately, I came up with that idea only once we were halfway through the process, but I found it actually quite helpful.
Yeah, it's also interesting how the handwriting is also telling you something if they cross out or something. Yeah. So and just to give you, because we Tina said we should give you really an example how coding. This is how we did the coding. So you see the number, you see the student group, and what instruction they had and what answer they gave and the reasoning. And then we coded like they're using continuity, they use Bernoulli, and they use some sort of pressure argument, or it is not clear at all. And so we gave these letters for each student. This was the coding. Okay.
So regarding the methodology, would like to know what were the opportunities and challenges in the application of the research methodology. Christian already pointed out to a practical way that you can use printed out answers and sort them. But is there anything else to know?
Okay. When you use written statements from the students in the form of these written quizzes, it's important to keep in mind, it's pretty obvious though, that you can't use follow-up questions. If I do an interview, then if what the student tells me is difficult to interpret, and I'm not sure whether I can capture what he or she is thinking, then I can pose a follow-up question, ask the student to elaborate a little more. All that is, of course, not possible in a written quiz. You can also not ask a question that maybe goes a little deeper, as I would in a semi-structured interview where I find out that the student has sort of a particular idea and I want to probe that a little more deeply. In some cases, and you saw the example of student response 4, where lots of things are crossed out, the interpretation of the student answers is not easy, and sometimes does remain unclear in the end. We sort of took our best guess and thought, well, the predominant idea here seems to be this, but there may also be a little bit of another idea playing into this, treating fluids as a single particle, but at the same time also making assumptions about the pressure and so on, which for us at first were different codes, but may not be completely separated in the students' minds. And one indication of that is also the third point that Claudia mentioned before, that students answer over different questions, that they answer the two different questions were not always completely consistent. Also, we ask students on these written tests always to explain their reasoning about the answer, which is essentially a multiple choice answer. And some students simply don't do that for lack of time or lack of interest or whatever.
So then another question, if you look back now, would you choose the methodology again? Could you have used other methodologies that would have maybe relieved you from some issues, but then maybe caused others?
Yes, I mean, briefly, interviews would have been helpful. One could have used them in addition. In some studies, we've actually done that the other way around. First, done some student interviews with about 10 students, maybe up to 20 students. And then after we've sort of gathered a broad idea of how students are thinking about a certain issue, put that into a written form and pose a task to them that very specifically can then trigger certain ways of thinking. In this case, we had the opportunity to do the quizzes. We did not really have the resources to carry out interviews beforehand. So certainly quizzes is better than nothing, and we decided to go ahead with that.
Jan, you've got a question.
Jan.
Yeah, thank you so far. I was wondering if you would do these in the interview format, would you then interview 2 students at a time? Because apparently the peer instruction seems to be a good remedy to get students to the next level of understanding, and then you could catch that maybe.
That's an interesting idea. What I have not done in the past is group interviews for the reason, despite of what you said, that we try to separate the sort of the diagnostic and the treatment, if you want. So we do the interviews and possibly the testing primarily with the intent of understanding better how students are thinking. And the treatment part, so to speak, we do then maybe not in the same semester, but in subsequent semesters by having peer instruction questions in the lecture or having something we favor, the tutorial worksheets, where students are led through a multi-page worksheet to sort of discover things on their own step by step. And that's very helpful. And it's based on the principle that you mentioned, that students talking to each other often can help each other out, can figure things out together much better than one alone. But we specifically try to separate that from the sort of diagnostic research part, which isn't necessarily, you necessarily need to do so, but that's how we do it.
Okay, thank you. It's a good order, I think, yeah.
Okay, go ahead.
I was wondering, as you realized with this written investigation, that contradictory to what your expectation was, there was no consistency in the wrong answers of one student. So I was wondering if you would have done interviews. Do you think you would have realized the same, or is there a danger in doing interviews that you expect a student to have a consistency in the arguments, and by doing the interview, you are not really able to realize there is no consistency? You know what I mean?
I hear you. You would wanted to answer that?
No. It's
Okay.
just We're running out of time, Christian.
Okay, let me try a very quick answer. I think that's a valid point. It depends on the interview tasks that you use, and you may spend only a considerable time on a single task and not see how a particular student would answer about a different question. That's true. I would think that you get a variety of ideas of students from the fact that you interview several people, more than one. But the lack of sort of a consistent picture may become more apparent in the written testing actually than in interviews. It also talking about what underlying model of student behavior one uses here. It shows you what we saw here. It shows you the limits of the misconceptions approach, because the misconceptions approach is often sort of taken as students have a very rigid idea of something that is not correct. And I think that's not what is meant by the term misconception. I see that as a more fluid thing, but certainly that would not be correct to assume that students have a particular clear alternative theory that they apply in all situations, partly because that alternative theory may actually be contradictory in itself, and therefore can't be applied everywhere. Should we?
Yeah, so Christian and Claudia is just warning that the official time for the seminar is someone added. So maybe it would be interesting that you pick like one part that you would like to talk about. And then people that can want to stay longer to discuss more, that they are all, of course, welcome that, but then we can close it with a little bit of a finding or whatever.
Okay. For us, it was the most important that you get the clue of how we worked. That because the other things there in the paper, that's why. So you get a taste on how you can analyze student thinking, and it's really worth looking at the tutorials as well. So our main findings can be found here. It didn't work. What you also find out, the lack of understanding of conservation of mass, and we have found also more general difficulties they have. I don't go into details here too much. And implication for practice. Continuity is not automatically understood by students and does need specific attention during instruction. And mental activation of students on relevant questions seems to improve student abilities to correctly answer and explain. So we do just-in-time teaching. And what our ultimate goal is to do tutorials for fluid mechanics that take into account these misconceptions. And that's why we analyzed different type of thinking, so we can address this in the tutorials. And also, if they do the right cross, it doesn't mean that they also think correctly. And it doesn't help to have just cookbook type laboratories because they do not change student thinking. Yeah, and maybe Christian, last sentence.
Okay. So one question was, how could others follow up on this? I mean, certainly you can follow up in terms of research, probe more deeply into student thinking about this particular topic, extend the topic to other issues in fluid flow beyond continuity. Some of that has been done already in terms of Bernoulli's principle. Investigating the application of the same or similar ideas in other fields is something that we have started at Hamburg University of Technology. The idea of continuity, the principle of continuity, shows up in other technical fields, even in logistics and transport. And one can then use results to develop instructional materials. We also had a take-home message. We originally had planned to ask the participants, but I think in the interest of time, we'll show you what we thought are the main things to remember. And maybe we'll just leave the audience with that.
So
thank you.
Thanks a lot, Christian and Claudia, for this interesting presentation. Maybe the final word I want to give to Esther, who's going to announce the next seminar.
Yes, thank you very much. And thanks everybody for staying here. Then our next seminar will be presented by the winners of the best research paper from the SEFI conference last year on the topic of analyzing student-teacher interactions in challenge-based learning. I'm just putting in here the link to the paper, which is in the proceedings, and a little homework for those of you who want to come along. Date to be announced soon, we hope. We're just trying to finalize and pin the dates, but it will be sometime May or June. Okay, so we'll keep you posted with that, and then we'll send you an invite again. Okay, later. So thanks everybody for attending, and back to you, Tine.
Yeah, I think for the ones that want to stay around to ask a question, feel free to do so. But we were all very happy that you were here and that you were interested in the seminar provided by our special interest group and of course by our speakers. So let's give them a final round of applause to thank them for the seminar.
Yeah, thanks very much. Very interesting.
Thank you.